looked into when we finished off last lesson. What was that?
Was it the ricer table that we looked at last week?
Very good. But the rice table itself is used to calculate something. What is that?
Was it equilibrium constants?
Good, right? Jacob, what letter do we use to denote the equilibrium constant?
K.
Very good. And Sid, what does the equilibrium constant K tell you?
Which side the equilibrium lies on?
Very good. So if you had to say it in 2 words for me, what would you say?
Equilibrium position.
Very good. That's exactly what I need here, right? So now all of you should ideally understand what K is, the general principle to find K, which is the rice table, and what it actually tells you, which is equilibrium position. Now, very quickly, Zen will remind us, what does equilibrium position lying to the right mean? What does equilibrium position lying to the left mean? Start with the first case. So Zainul, equilibrium position lying to the right. What does that mean to you?
Oh, sorry. From what I remember was if equilibrium position lies to the left, the reactants will have a greater concentration than the products, and if it lies to the right, the products will have a higher concentration than the reactants.
Very good, right? Very good. You're nailing it. It's good to see you're all doing your homework and you're being consistent, right? That is literally the secret. Now, as I said, you have access to all the trial questions at the bottom of this booklet. So I would highly advise you all start doing that now. But very good. You're doing well so far. Now, before I jump into today's lesson, which is going to be much more upon K, we're going to be doing some harder questions. Does anyone have any questions from class that you just want to posit and throw out there? Anything that confused you? It can be ahead.
Yeah, I just had one.
Oh, okay. We'll start with Sid, and then we'll go to you, Zainul. Sid, question?
Why doesn't pressure affect the KEQ?
Why doesn't pressure affect the KEQ? Very good question. I'm going to come back to that because I did explain that why it was temperature that affects KEQ last lesson. So I want to see if any of the other students can help you out first. But Zainul, what was your question?
It's the exact same question I said.
Great minds think alike, and you're both thinking the same, which is good. All right, so let's start with Sid, right? I want someone to help Sid out and answer his question. Jacob, we'll start with you, right? Now, Jacob, let's just say we're talking about the Haber process. Can you remind us what the equation is? I always like to talk about Haber process because at the end of Mod 8, you have to know one industrial chemical reaction very well. Haber process is bread and butter. So, Jacob, what is a reaction again? For the Haber process?
It's just N2 plus H2 gives NH3.
Perfect. Nice, right? And we're going to put a 2 here, and we're going to put a 3 there. All gaseous. Exothermic equilibrium. That's the other principle to remember. Triangle H equals -92 kilojoules. Well, right? Now, let's say that this is our initial concentration of gases. I just randomly plotted lines here. Let's say this is our H2 here. Let's say this is our N2 here. And let's say this is our NH3 here. Right? Now, do you all agree right now? Actually, you tell me, is this system at equilibrium at time equals 0? Concentration time graph. So Akshita, is it at equilibrium or not?
No.
Britannia, is this system at equilibrium or not?
Yes.
Yes and no. Sid, confirm it for us. Equilibrium or not?
Yes.
Yes, right. If you have constant concentrations that are not changing, it's telling you the rate of production is equal to the rate of destruction. That is the definition of equilibrium, right? So system's at equilibrium now. So if I asked you to calculate K, Sid, what's the K expression?
Reactants over products.
Reactants over products?
No, products over reactants.
Okay,
Yeah.
So product is NH3, and what are you going to do to NH3? What power are you to bring it up to?
To the power of 2.
Good. You're going to raise it to the power of this stoichiometric ratio, right? Good. And we have 2 reactants. We've got our N2 and we've got our H2 here. And we're going to cube the H2, because there's a 3 in front of H2, that's a stoichiometric ratio. So that's our constant. Everyone with me? So these values, X, Y, and Z, whatever they are, we sub that into that formula, we'll get a K output. Everyone with me? Now, Sid, let's say I double volume. What will happen to pressure?
It will decrease.
If I double volume, what exactly will happen to pressure? I want a specific answer.
Pressure will half.
Very good, right? Does everyone agree, right? Pressure, volume are inversely proportional, and the concentration of a gas is its pressure. C is P for a gas. Makes sense, everyone? So since I've doubled the volume, the opposite change is halving the pressure. So all of these pressures would immediately drop down to half whatever the original value was. If this was 2 units, it would drop down to 1. If this was 8 units, it would drop down to 4. Makes sense? So what's going to happen is this sharp drop that we see here. Drop down to here, it'll drop down to there. This might drop down to around here. Now, actually, I thought, what does the Chatelier's principle state? Give me an exam answer.
Okay. So Le Chatelier's principle says that at dynamic equilibrium, if it's disrupted in changing conditions, the position of equilibrium will like counteract to the change to reestablish an equilibrium.
Good, but you can make it even more concise, right? So the goal here is to use it as least fancy terms as possible to communicate the point. And the essence here is a system in dynamic equilibrium, when it's subject to any kind of disturbance, it'll partially counteract the change, full stop. And that's how it reestablishes equilibrium, right? So what's going to happen now that I've doubled volume? Now, Zeno, what are the 3 questions we always ask ourselves for equilibrium?
Stimulus, opposition, and direction.
Very good. So tell me, break it down for us. What was a stimulus? What is the opposite of that? And what direction will this reaction go?
The stimulus was change in, I think, decrease in concentration. And the opposite would be increase in concentration.
I would say, when you say concentration, everyone, concentration refers to one species usually. So if I say I have increased concentration, you need to say of hydrogen or nitrogen or ammonia. When we say pressure, you're implying you've changed the concentration of all the gases. So I would say the stimulus here specifically is a change in pressure. Make sense, everyone? Even when you change volume, link it to a change in pressure. That is a stimulus when it comes to gases, right? So we've halved the pressure, Zainul. So we've decreased pressure. We want to increase pressure. Are you going to favor more or less gas moles?
More.
Good. So which direction are we going?
To the left.
Good, because we've got 4 moles on the left-hand side versus 2 on the right-hand side. So what you'll end up seeing is this hydrogen will start to go up. This nitrogen, that was a hydrogen, our nitrogen gas, also here, will start to increase as well. And our ammonia, in the same essence, will start to slowly decrease, right? And what you end up seeing is, coming back to Sid, we had a K constant that was determined from this value, and this value, right? Now, what's going to happen is when we disturb the equilibrium, you can see that the system reestablishes or changes the concentrations. And the way I think about this is the system is trying to change the concentrations in an effort to maintain and reestablish that K value. The direction it shifts all of that is to change the numerator and denominator values to reestablish K. So what will end up happening is this initial disturbance here, when all these gas concentrations change, it's going to be altering the K value, and then the system will shift, which is all of this change, to return to that normal K value, which is temperature dependent. The only time in which K is affected or changed by stimulus, Jacob, is with what example?
Temperature.
Very good, right? With temperature, the issue is when you change temperature, you don't immediately change K, unlike pressure. Did you see when you change pressure, you change all the concentrations, you immediately stuff the K value up, and then the system tries to readjust to return to K. With temperature, when you change the temperature at this time point, you're not changing concentration immediately. What instead happens is you affect particle collisions, and the reactants might go up and the products might go down. And now you can clearly see, mathematically speaking, these numbers have changed from there to there, and hence the K value would have changed. Does that make sense, Sid? So the reason that temperature is the only value to affect, or disturbance to affect K, is because temperature doesn't immediately affect the concentrations of any of the gases. The equilibrium shifts to change the temperature, whereas with all the other disturbances, the disturbance itself changes all concentrations, and the system will readjust to restore K.
Yeah, I got that.
Yeah, good. All right, now let's move on in the interest of time. I want us to go straight and start doing some harder K constant questions. Now, question, when do you use a rice table? A lot of year 12 struggle with this even until halfway through next year. I still see students ask, when should I use a rice table? So for those of you who have been doing rice tables at school, can you hit the raise hand icon? Because what I'm going to do now is I'm going to take you straight to trial questions, and we're going to smash out trial question after trial question. There you go. Didn't even have to look, and I got a K constant question. All right, Rathania, when do you use a rice table question? Or when do you use a rice table for a chem question?
You can find unknown concentrations through rice tables.
You can find unknown concentrations, yes. But I'm asking you, in this question here, read the question out for me, everyone. You do not say, you don't see here that it says, please use rice table. And you realize the more chem content you learn, the more the rice table takes a backseat in your knowledge, because you're learning so many other things. You're going to be learning KSP, the solubility product, ionic substances, dissociations. So when you see an exam question, Jacob, when do you know to use a rice table?
I think you use it when you're not given the concentration at equilibrium. So if you're given the concentration of all like the reactants and products at equilibrium, you just chuck it into the K expression. But if you don't have that, then you use the rice table to figure out the concentration at equilibrium.
Very good, right? I think that's a very logical, reasonable approach. Chemistry, guys, is just logic. There is no fancy, super difficult questions. The whole year is going to be about developing principles on how to approach questions. Be given a question you've never seen before, you apply those principles, you get 4 marks. And the people that do that really well, state rank in top chemistry. That's it, right? And it requires a little bit of 2-unit maths. That's it. Now, I really like Jacob's proposition, and I'm just going to be reframing that very slightly, which is I always think to use a rice table. First of all, if they ever ask about K, if they ever ask you a question about K, you should be considering a rice table. But the definitive way I 100% know I need to use a rice table is when they give you concentrations. I want you all to write this in red. Concentrations at 2 different time points. 2 different times. Where do you see that in this question? So, Zeno, reading this question, where are the 2 different time points you're given? Zeno, I've highlighted 2 different time points. Can you just explain to the class what the 2 different time points are?
Is it one before equilibrium is achieved and one's after equilibrium is established?
Good. And usually 99% of the time, right, it's going to be one circumstance when time equals to 0, aka just when the gases were added to the vessel, because that's time 0, right? That's exactly when the reactants are in the vessel. They haven't even collided yet to form product, which is what you guys see here. Hydrogen gas was inserted into a 1-liter vessel with iodine gas. Now you need to visualize this. Imagine you stop time the second the hydrogen and the iodine have been added to the vessel. That is time equals 0. Then what you've been told is after some time, after equilibrium has been reached, T equals equilibrium, you're given other bits of information. And so straight away I know, now since I have two different time points, I've been given initial and equilibrium data, I need to do a Rice table. Does that make sense? So from now on, I'm going to ask this multiple times because they always just, all they do is change the wording of the question and the data. Everything else is going to be the same from now on, right? This is when to do a Rice table. Now, everyone fill me in on this Rice table. So have a read of this question. And I'm just going to be writing Rice, and I'll be asking you guys to fill this out for me. Now, let's start doing a bit of chemistry calculation principles. Whenever I see a HSC chemistry question, Britannia, what is the first thing you want to make sure is written on that page? And if it isn't written on the page, you will be writing it yourself. The most important thing.
Balanced equation.
Very good, right? So the first thing in any calculation question you learn, I don't care if it's titration, I don't care if it's KSP, I don't care if it's this stuff. First thing you need to tell me is, has an equation been written? And if not, you're going to be writing the equation. What is the second thing that we'll be doing? Now, I don't expect us all to know this, but the second thing I want you to do is I want you to turn this, all of this stuff, right? This is crap. It's all English. We're not doing English, right? We're not studying literature, we're studying chemistry. I want you to convert all of these words into data for me. What is N? What is M? What is C? That's what I want you to tell me, right? So I want us to do this right now. So I'm going to ask Akshita, go across the lines. Whenever you get a data point, tell me, what is N, what is C, what is V? What's the first data point you see in this question, Akshita?
A sample of 0.0123895 moles of hydrogen gas was inserted.
Okay, pause right there. What is the data from that point?
0.0123895 moles of hydrogen.
Good, but do you agree when you say of hydrogen? We don't know if you're talking about C, concentration, volume, mass, temperature. What are you talking about, Akshita?
The concentration.
Think very carefully. What is the unit that you see here? Is it moles per liter, which is what concentration is?
No, just moles.
Very good. So a strong student would write N bracket H2 is equal to 0.0123895. Now, when you do this, what you'll realize is your brain straight away goes, N. What formulas do I know has N in it? And you'll straight away be thinking formula like C equals N on V. That's what writing data does. It starts propelling some momentum in this question. What else have we been given? We've been told N of H2 is this value here. What other data do we have? So it'll finish it off for us.
Your mic cut out for me. What did you ask?
Finish off the rest of the data for us. What else do we have?
We have the volume,
Good.
which is
V.
1 liter.
Good. I want you guys to say it to me in
Okay.
formula terms, V and C, right? So we know V is equal to 1 liter. This is helpful because now we've got an N, we've got a V. Obviously, what do we need to find, everyone?
Concentration.
Very good. You straight away think C equals N on V. So you're being guided to find C. You can see how easy these questions get when you do this. Good. Sid, keep going. What is the other data that we have for this question?
0.008705 moles of I2.
Good. So I want to hear N of I2 is equal to that value. Okay. Good. N of I2 is 0.0087805. And feel free to write this data underneath the exact substance. So you could write that underneath I2. You could have written the H underneath H2. That's good to do. But I'm just writing it generally for now. Good. What else do we have, everyone? Akshita, keep going.
Was it the concentration? So
I want a letter.
of
Very good. Good. Keep going.
C of hydrogen iodide, which was 0.0154450.
Good. Now, when you write this, you'll realize what Band 4, Band 3 students would struggle on with this question. They will sub in the N values into the rice table and the C values into the rice table, which won't work out. Jacob, when we're doing a rice table and when we're finding K, what units are we subbing in for products and reactants? Jacob?
Sorry, what units?
Yeah.
We're
Leading to
going to
K.
be using concentration, but K isn't going to have any units.
Good. K doesn't have units, and the concentration will be in moles per liter. So what I'm trying to get at here is to do a rice table, you need to only input moles per liter data, right? So let's start off by writing our little ratio. We know the ratio is 1 to 1 to 2. I'm just writing it directly underneath the substances. What is the initial concentration of hydrogen? Now, to help us with this, I'm going to help you by adding on a little bit more information. I like to write N of I of hydrogen. So this tells me this is the initial number of moles of hydrogen that I have. So if I have Ni of hydrogen, initial number of moles is equal to that in a 1 liter vessel, I want someone to quickly calculate what is a concentration of hydrogen initially. So you always write the entire formula first, C equals N on V, and then sub in the data points. So it's going to be 0.0123895. It's in a 1 liter vessel, so it'd be the same value there, right? So this question isn't too tricky, but in other questions, it's 2 liters, 3 liters, change your outcome. Good. So now we know the initial concentration of our hydrogen, which is on the left-hand side, is 0.0123895. What else do we know about our initial concentrations? Sid?
Iodine. So you could do C, I2, yeah. Just over 1.
Good. And Sid, what's the initial concentration of hydrogen iodide?
We do not know that yet.
We actually do. I want someone to think about this and tell me, what is the initial concentration of hydrogen iodide? Use your imagination, guys. We're talking about time equals to 0. Read the question really hard and tell me
0.
what is. Yes, exactly, right? At time equals to 0, all we've done is we've added some hydrogen particles, some iodide particles, and they haven't even had time to collide. No successful collisions, there is no product. This is often the case with these questions. They add 2 reagents at time equals to 0, and you have to know that time equals 0, there is absolutely no product. Okay, good. Now, what about this change? Now, we've been told after equilibrium was achieved, hydrogen iodide was found to be 0.0154445. 15445 moles per liter. So we know the change in concentration was 0.015445. How much should the other gases change by? Say no?
Would it be the same?
So Zainul, when we're talking about those concentration time graphs, what were the 2 phases of disturbance? Come back up here for me. What are the 2 phases of disturbance that you can see in that circled area of the concentration time graph?
Temperature?
No, so the 2 phases was the stimulus phase. Do you remember that? And then shortly after that stimulus phase, there was a counteraction phase where all the gas concentrations changed and re-established equilibrium. Now, I said one very, very important thing about this counteraction phase. What did I say?
The molar ratios.
Very good. Can you just elaborate on that, Jacob? What follows the molar ratios?
The concentration.
The change in concentration.
Yeah.
Does everyone see these changes in concentration that are happening from the disturbance point until the new equilibrium has been established? The change in concentration of all substances must abide by the stoichiometric ratio. Okay. Now coming back up here, the same thing applies for C in rice tables. The change in concentrations of gases, solids, liquids, whatever substance we've got, must abide by the stoichiometric ratio. Okay? The only difference is for solids and liquids, they don't affect K, so we don't have to care about them. But every other state, change abides by stoichiometric ratio. Now, Rithania, what number is in front of hydrogen iodide in our stoichiometric ratio?
2.
Good. So you're going to write 2 parts in my cooking recipe. Your stoichiometric ratio is 0.015445. So Rithania, how much is 1 part in your calculator? Can you tell the rest of the class when you get it?
It's 0.0077225.
77225, right? Now, very important thing with chemistry, I haven't taught you this yet. Does everyone know how to store values on a calculator? Can you hit the raise hand icon if you know how to store values on a calculator? Good. Good. Jacob, have you learned how to store values on a calculator?
I forgot.
That's all right. So what you do is you press shift, the shift button, and what that does is it will change all the keys to the yellow text that's right on top of it. Do you have the Casio standard calculator?
Yeah.
Okay, so the first thing, this is for everyone, if you want to store a value, the first thing you press is shift. So imagine you're storing the number 2. Put 2 on your calculator, then you press shift, and then you need to look for the button that has STO for store. Right? Once you find that, you press that button STO, and then you can pick, you'll see in red letters on top of buttons, there'll be an A, B, C, should be a D, should be an X, and a Y. That was on our calculator 6 years ago. I don't know if you guys have some fancy new one that you can use, but more or less should be the same, right? So then you just press shift
I got it now.
and A. Yeah. So now you've stored it as A. And then to get that value back, if you ever want to use it, you just press alpha and then A. I think alpha is the button.
Yeah, it is. Yeah.
Good. Sid, question?
I did that in my prelims, and then my teacher just questioned why I had like A in my working out.
Teacher silly.
Yeah.
No, that
Okay.
makes no sense. You definitely can do that in the HSC. You should do that. And if you don't do that, your answer rounds off a little bit every single time you do another calculation and you don't store it. The only thing you need to do, Sid, is when you calculate, let's say you found this, you put an arrow like this and you put A. And that will show the marker you're referring to A, you're referring to that number from now on. If you do that, from then on, you can just use A instead. Does that make sense? You need to store in chemistry. So very important for everyone. If you need to store until you get to your very final answer, and then we're going to talk about rounding as well. There are important principles in how to round in chemistry as well. But you must store. Otherwise, your value comes up a little bit every single calculation, and your final answer will be way off the true value, right? Good. So we've stored this as A. We know 1 part change is equal to A. So now, how much would the reactants change in concentration by? Well, actually, are they products or reactants? H2 and I2.
The reactants.
Good. Now, the product increased in concentration. What should happen to the concentration of reactants?
Decrease.
Very good. So we're going to put a negative sign. That's the first thing. Now, how much should they change by? A or 2A?
To A.
So remember, everything changes according to the stoichiometric ratio. HI increased by this much because this value, 2A, is represented by 2 parts in our cooking recipe. H2 and I2 have 1 in front of them. They're only going to ever change by 1 part, not 2, right? So just like you said, they will decrease, but instead of decreasing by 2A, since they have 1 in front of them, they will change by A. Does that make sense, Akshita?
Yeah.
Good. So you're just going to write subtract A, subtract A. So everyone tell me, what's the final answer? What are the final equilibrium concentrations of H2 and I2? Of course, you're going to store them. You'll store this as B, you can store this as C, but just tell me, what are the numbers that we get?
For I2, I got 0.001058.
0.001058. Very good.
And then H2, 0.004667.
So very good. Good. So you can store that as BC, whatever you'd like to store it as. And the final thing is just subbing all of this into K, because once you get equilibrium concentrations, you can always find K. Okay, good. So now we just write our expression. We already know what is our expression? Going to Ritanya, what is the expression for K?
HI to the power of 2.
Yep.
And then I2 times H2.
Good, right? And when you sub all this in, you're just going to be subbing in 0.015445 squared. And for I2, you'll be subbing in B. For H2, you'll be subbing in B. So B here, that's H2. And for I2, you'll be subbing in C. B times C. I'll sub in the values directly, right? But make sure you're using the exact values. So what's our final answer of K?
48. 2 sig figs.
How many sig figs? Let's talk about sig figs. Sid, could you just remind the class, how do you round off in HSC Chem?
You get the number with the least amount of sig figs.
Why do we do that, Sid? Why do we round off to the data value we use that has the lowest sig figs?
To limit like calculation error, because if one is like 7 sig figs and one is only 2, it like creates differences.
Yeah, good, right? So your answer is only as accurate as your least accurate data point. So to explain that, imagine if I was calculating all of your BMIs, right? So let's say I used an electronic weighing scale and I got all of your weights to the nearest, I don't know, 1/10 of a microgram. That's how accurate I was. But then when it came to height, I just looked at you and I guessed your height as either being 1 meter or 2 meter. You can imagine your BMI values will still be very inaccurate because I used 1 sig fig for your height. And it doesn't matter if I use 10 sig figs for your weight or 20, your answer is only going to be accurate to 1 sig fig, which is a height that I guessed, right? So hopefully that analogy shows you. In chemistry, same principle applies. Use the lowest sig figs in the question and round off your answer to that. Now, in this question, Sid, what's the lowest number of sig figs you see? And what value is it?
1.0.
Very good, 1.0. That's 2 sig figs. Very good. Good. How many sig figs in this number here, Zainul?
6.
Good, right? So if you have a decimal point, it's only these numbers that are significant. Britannia, how many sig figs in 1,000?
Um, 4.
In maths, we say it's 1, 2, 3, or 4 because we don't know if they rounded it off from 1,001, which means those digits are significant and this 0 isn't, or if they rounded off from 999, in which it's only accurate to 1 sig fig, right? So in chemistry, we assume the worst case. So we just say 1,000 is 1 sig fig. Okay. What about 1,001, Jacob? How many sig figs?
4.
Very good, right? So zeros between numbers are significant. Very good. So coming back to this, we've got our answer. Make sure you write the full decimal place or whatever that was, and then you round it off and you show you've done that to 2 sig figs like this. Very good. That wasn't too bad of a HSC trial question, right? This is what you're going to be doing at the end of the year. Not too bad at all. Let's see if we can do another question. Okay. What effect would a decrease in temperature have on K? You'll have about 20 seconds to answer this. Hit the raise hand icon once you've got an answer. Good. Speak out loud if you helps understanding. Akshita, when you're ready, take us through your line of thought.
Right. So I remember you saying that temperature was the only one that doesn't really affect the product constant, was it?
No, so temperature, so to keep it very simple, temperature is the only variable to change K. Everything else will maintain K, and that's because that initial change is the disturbance that shifts you away from K, and then Le Chatelier's principle will allow all the reactants products to change their concentrations and return to K. Whereas in temperature, that's not the case. So T is the only factor to affect K. Okay, good. So keep going. So we know temperature is going to affect K. So we want to know whether it causes K to go up or down. What's your answer, Akshita? Line of thought, that's what I care about. I don't care if your answer is right or wrong. When it's exothermic, which side do you put heat? Left or right-hand side?
Right-hand side.
Good, so you put heat there. We've just said a decrease in temperature. So what are the 3 questions you ask yourself?
Stimulus, the opposite of it, and then the direction.
So we said we're going to decrease temperature. What's the opposite of that?
Increase in temperature.
So which direction do we go?
Left, was it?
We want to increase heat. Think of heat like a product. If I don't want to make more product, which way will I go?
Okay, right, yeah.
To the right-hand side. What does that do to K? K is just products over reagents, right? When you shift to the right, what happens to products? What happens to reagents?
So there would be more product.
Concentration, exactly. When you shift to the right, what would happen to reagents?
There would be less.
Good. So what happens to K?
Does it stay the same?
Use an example, right? You've got half, right? If let's say we've got 2 on 2, which is 1. If I increase the top number to 4 and I decrease the bottom number to 1, we've gone from 1 to what number?
4.
Good. So what's
There
happened to
would be
K?
an increase.
Good. Just fraction,
Fractions.
right? Numerator goes up, K will increase. Good. So K goes up. Very good. I'm sure. Hopefully everyone else. Did everyone else understand that? Did that make sense? Right? So whenever you're thinking about how K is affected, just ask yourself which way it shifts and then go back to the formula, which is products over reagents. What about C, Britannia? What's the answer for 28C? You have 10 seconds. And everyone else hit the raise hand icon once you've got an answer. Good. Britannia, what would pressure do to K? Does pressure affect K?
No.
No. So the answer is nothing. Zilch. 0, right? Very good. All right, let's move on. Let's do one more K question, see how you go. I want to give you a harder one. These ones are not too bad. How about this question here? This isn't a K question, but concentration time graphs, like I said, are very high yield. So question 14. When you get your answer, hit the raise hand icon. And in about 10 seconds after you digest the question, I'm going to start asking people their line of thinking. Okay. Some of you should have got an answer by now. Very good. Very good. Good. All right, let's start going into it. So I'm going to ask, actually, what happened at 15 minutes?
Was it the initial stimulus phase?
Okay, yes, good. So I'm
Yeah.
asking, what was the stimulus?
A sudden, like a change in concentration. So of fluoride.
Yeah, good. Be confident in yourself, right? You see, everything's gradually changing. That's the counteraction phase, right? If you draw a vertical line straight down, so get a highlighter, draw a vertical line straight down at that change, the key thing you see is this drops in concentration. So it's very clear that fluoride has been removed. Done. So you straight away can say C and D are completely wrong. In about 5 seconds, you all should have thought that. Now, 30 minutes. Ruthania, what happened at 30 minutes? Yeah, I'm drawing a vertical line. Ruthania, do you see a clear stimulus phase?
At 30 minutes, there would be a decrease in temperature because it's an exothermic reaction.
Okay, good. Sid, explain this further. So what are the 3 questions you ask yourself in any equilibrium question, Sid?
So the stimulus, opposite, and direction.
Good. In this one, you just don't get it in a linear fashion. So Sid, which direction did the equilibrium go?
It went in the forward direction.
Good, so shifted to the right-hand side. Now we know it's exothermic, so heat's in the product. Why would you shift to the right-hand side, Sid? To make more heat or less heat?
To make less heat.
Are you sure? Why would you favor to the right-hand side and favor the exothermic reaction, which generates heat? What are you trying to do?
So the temperature would decrease, so it'd shift to increase heat.
Good, right? So as Ruthania said, the temperature went down. Opposite of that is an increase in temperature. We want to favor the exothermic reaction to achieve that opposite, right? So we shift to the right-hand side. Very good. That's it. So your answer here should be Tanya. What was your final answer?
A.
Good. Good job. All right. That's 2. I think that's fine. Question 4. Hit the raise hand icon once you've got an answer. Then we'll do one more K constant question, hopefully a harder one, and then we'll move on. Does anyone know any examples of equilibria that doctors might have to know?
Homeostasis.
Yeah, so that's a more general equilibria, but no specific equilibrium is the example of carbonic acid, right? So when you breathe in carbon dioxide, it dissolves in blood and it forms carbonic acid. And that carbonic acid dissolves in water and it does this, CO3 2 minus, right? And it forms an equilibrium that maintains a pH of 7.35 to 7.45, right? In type 1 diabetes, people can't use their sugar. So what they do is they burn fats instead. And a side effect of that is they make what's called ketones, which are very acidic. And as you can imagine, what do the ketones do? They raise the hydrogen ion concentration in the blood, right? Because that's what acids do. And so this entire equilibrium will shift to counteract that change to keep your pH within this range. And the second it falls out of this range and it becomes too acidic, you become very sick, you can fall into a coma. So as doctors, understanding this allows us to treat a patient, giving them bicarbonate, etc., to treat their acidosis. So we use chemistry here and there. Understanding these principles is very important, especially in the medical field. Good. Coming back, answering this question, hit the raise hand icon once you've got an answer. Good. Ruthania, we'll go to you. Question 4, System 1. Actually, Ruthania, you've answered quite a few questions, so good job. Jacob, we'll go to you. If we doubled the pressure, Jacob, what would this system do?
Yeah, so if you double the pressure, so for the first system, there'll be no change because the ratio is 2:2. And then for the second system, it will shift to the side with the least amount of moles. So it will shift to the right. So it has to be A.
Good. Now, Jacob, when you're writing your exam answer, what's one thing you definitely want to include when you're explaining pressure changes?
Le Chatelier's principle.
Good, but there's one thing that students
Volume.
Close. Pressure is the main thing, right? So if they
Okay,
give you a
yeah.
volume question, if you link it to pressure, perfect. If they give you a pressure question like this, you don't have to talk about volume. So pressure is the disturbance that we care about in terms of LCP. Sid, what do you think students, band 4 students, band 3 students would forget that none of you are going to forget?
Concentration.
Yeah, you don't need to talk about concentration. What I want to hear is that you compare the number of gas moles on the left-hand side versus right-hand side in your explanation, right? So something along the lines of the Chatelier's principle predicts when the pressure of a system is increased, it will shift to decreased pressure by favoring fewer gas moles, brackets, in this case 1 mole on right-hand side versus 2 moles on the left-hand side, right? So a strong answer would have that as well. So make sure you write in red, include gas moles LHS versus RHS, okay? Good, all right, good job. So it is going to shift to the right. And so your best answer would be A. Good, very good. Let me find you all a tough K constant question. Definitely should be one here. Load up. Yeah. Yeah, nice. Okay. Okay, we did question 22, A and B. This is a hard one, so I want you to read the question and come up with a plan of attack. What do you plan on doing to get your answer right? So I want you to imagine you're in reading time. This is your HSC Chem 2023 exam. This is a question you read. Do you have a plan of attack? In about 10 seconds, I'm going to ask people, what are you going to do to get to your answer? Good, Zainul's got a plan of attack. That's the most important thing, plan of attack, right? Do you know the steps you'll take to solve the question? And if you don't, I'll show you how to break down any question. It's not too hard in Chem. Okay. Zainul, what's your plan of attack?
So first of all, we've already got a balanced chemical equation.
Good.
We've written the expression for it, and for C, the first thing I would do is write the information that I have. Then most of it we're given the mass, so we need to convert it into moles to determine the concentration of each product and reactant.
Very
And then
good.
I would substitute it in to find the value of K.
Okay, good. So you substitute. Would you use a rice table? Zainul, rice table?
Yes, because we don't know the concentration of CF4.
But how would you know if it's in equilibrium or not? Let's say you get K is equal to 0.7.
that's greater than the K that was given, so it might not be in equilibrium.
Perfect. Perfect interpretation. Did everyone hear that? So, you know, the whole point about temperature being the only factor to affect K, the reciprocal or inverse is also true. There is only one K value that a system can have at a particular temperature. So in this specific equilibrium, right, where we've got CO2 plus CF4 gives you COF2. I haven't told you the temperature, but whatever temperature this system is, they've told you that the K constant is 0.5. The equilibrium constant, which is K, is 0.5. So we know, no matter what, at this temperature, K will always be 0.5. Let's just say the temperature here that we're studying is 0 degrees Celsius. So at 0 degrees Celsius for this reaction, K will always be 0.5. If K is not equal to 0.5, the system is not in equilibrium. Okay? And we'll talk about what that means shortly, but I want you guys to solve this question for me. To solve this question, hit the raise hand icon. I'm going to give you guys about a minute. Okay? Good. Get started. I'll give you all about a minute, minute and a half. So get a final answer and hit the raise hand icon once you've got an answer. Good. Meantime, I'm going to quickly pick up my lunch from the ground floor of my apartment. I'll be right back. Okay, good. Did everyone get an answer for this? So let's start off with Sid. What have you gotten for your answer? Start off with the data, Sid. What data do we have?
So we have the mass of CO2 initially and the initial mass of CF4.
Good. So we're going to write M of CO2I is equal to 5 grams. Or in fact, you can write the equation again. I'll show you the most optimal way to do this question. So write a big equation widely spaced apart like this. 2COF2. Make sure that you've got it all in gaseous state. Good. So you're going to write here, little m CO2I is equal to 5 grams. Little m of CF4I is equal to 29 grams. What else do we have, Sid?
We have the volume of the
Good.
vessel.
You're going to write V is equal to 5 liters, right? In fact, I like to write this separate up at the top. That's because that's V for the entire system. It doesn't matter what substance we're talking about. That gas is spread out in that 5 liter volume. Good. So actually, what are the next steps? Actually, we've got another data point here. C of F2 was found to be 4 grams per liter. So Akshita, what time point is this?
This isn't the initial one, so it's after. So you wouldn't write it next to where we wrote it, so you would write it in a second row, probably.
Yeah, so let me just confirm. I've just written the equation slightly wrong. It should be CF4. Okay, good. Yeah, so you can write. What letter is this actually? Is it M, N, C?
So I think that's concentration. So that's
Very good. Just a slightly different one. It's M on B.
Yeah.
C equals M on B. Still concentration. So I'd say C of CF4. This isn't initially. Is it at equilibrium, Jacob, at that point? We don't know. Do we all agree? Right? There's 4 grams per liter. The core question is asking us, is this mixture at equilibrium at that point in time? And we're answering that question. So I'm just going to put time 2, right? You can write T2, something along those lines. And that's equal to 4 grams per liter. Good. So, Brittany, what do I do now?
Convert the masses to moles.
Good. So N of CO2, N of CF4. These are the initial number of moles. So what did you get, Brittany, for initial number of moles?
For CO2 was 0.11361, and then it just continues. So I stored it as A.
Good. Keep going.
And then CF4 was 0.32950.
Yep, store it as B. Very good. What do I do now?
Put it into the ice table.
Not quite. You cannot put number of moles in an ice table.
Concentration.
Very good. So let's go to Jacob. What are the concentrations of these gases?
So for CO2, the initial concentration is 0.02272 moles per liter, and then CF4 0.0659 moles per liter.
Very good. Store it as D. Good. So now we're ready to do a rice table. Now, after a while, you get to the point where you don't need to put an R, but we're not there yet. I want us to get very confident with our rice tables before we exclude the R. I think it's good practice to always have R for that matter. So I'm just going to write it here. 1, 1, and 2. Okay? Because the R, what does it affect, Sid? Does it affect the initial concentration, the change, or the equilibrium?
The change.
Very good. So I want all of us to remember, that's why we write the R, so we know what to divide by 2, to multiply by 2 based on the stoichiometric ratio. Good. So we know the initial concentrations of CO2 is C. We know the initial concentration of CF4 is D. What is the initial concentration, Zainul, of COF2? Zainul, COF2. What is the
Would it
initial
be
concentration?
0?
Very good, right? Now, what do we get after a period of time? We get told the concentration of CF4 is 4 grams per liter. Zainul, how are you going to change that to moles per liter?
Oh, sorry, what was the question?
How are you going to change grams per liter into the correct units that we care about?
C is equal to N over V.
Sure, so do it for us. How did you do this?
I wasn't up to that yet.
Okay, that's all right. Anyone get up to this? Good, Sid, take it away.
I just did 4 times 5 to get the moles, the mass, and then find the concentration through that.
Yeah, sure. So basically, there's many ways to do this. I'll show you the way I like to do it as well. But what Sid did was he went, well, this is 4 grams per liter. We're using the formula C equals M on V, right? And we're trying to find concentration in moles per liter, right? So I see what you did. You did M equals to CV, and you would have multiplied the 4 grams per liter times 5 liters to get to 4 grams. And I'm guessing, so did you convert that to moles, and then did you divide by 5 again, something along those lines?
Yeah, that's what I did.
Sure, that's a little bit of a long way, as you can see, because you multiplied by 5 and then you divided by 5, right? So a slightly easier way to do it, guys, is think about the units you have and the units you want. You've been given data in grams per liter. We care about moles per liter. So a simple thing you can do is fix the moles and just convert grams to moles, right? What I mean by this is we know in 1 liter, we have a mass of CF4, which is equal to 4 grams. What is the number of moles in that liter? That's what concentration is, right? So we're going to, therefore, number of moles is equal to mass on molar mass, which is equal to 4 divided by 12.01 plus 4 times whatever fluoride is. What do we get as our number of moles of CF4 in 1 liter? Can anyone tell me?
I got 0.04092.
0.092. Good. We're just going to store that as X, or whatever you want to store it as, right? So therefore, I straight away know in 1 liter, I have this many X moles.
Oh, actually, wait, no, that's wrong. That was after I used the molar ratio. It should actually be 0.04544.
Okay, good. 0.04544. Very good. So we'll store that as X still. We'll say, therefore, in 1 liter, we have this many moles, 0.045 or X number of moles, which means the concentration of CF4 is just X moles per liter. I just did the same thing that Sid did. It's just my way of doing things when I'm being asked to convert grams per liter or milligrams per liter to moles per liter. Okay, do whatever you feel comfortable with. Just make sure you always do the same way every time from now on. Okay, more times you do it, the easier it becomes. It starts to become like writing English at this point, right? Good. All right, so now we know that the equilibrium or query equilibrium, this is the thing, we don't know whether it's at equilibrium, right? We just know it's time 2. We know this new concentration is X moles per liter. Now just have a look at the numbers for me, everyone. The initial concentration was 0.06. It's dropped down to 0.04. What has happened to our reagent, Akshita?
Sorry, could you repeat that?
What's happened to CF4? Has it gone up or down?
Down.
Very good. It's gone from 0.06 to 0.04, right? So it's decreased. And so the other reagent will decrease and our product will increase. How much did it decrease by? Can anyone tell me what's D minus X? So the initial concentration of CF4 minus this query equilibrium concentration of CF4. What did we get?
0.02046.
Good. All right, let's just store that as Y, right? Whatever you like to store it as. I'm just going to subtract by Y, subtract by Y. So now I know the equilibrium or query equilibrium concentration of CO2 must be C minus Y. And now I know that my COF2, how much must it increase by, everyone? So, Ruthania, how much must COF2 increase by?
Sorry, can you repeat that again?
How much must the product COF2 increase by? The reagents have decreased by Y moles per liter.
It'll be 2Y.
Very good, right? So we know 1 part in our cooking recipe is equal to Y. So sometimes, especially when you're starting off doing these rice tables, always write what is 1 part equal to. We know 1 part is equal to Y. We know that COF2 is increasing by 2 parts. It's going to increase by 2Y. That's it. So now when you sub this all into K, you're going to K is equal to, what's the expression for K? You would have already got it in the above question. So COF2 squared divided by CO2 times CF4. And when you sub it all in, it's going to be equal to 2Y bracket bracket. Remember the 2 is inside the bracket. And I'll make that mistake. CO2 is equal to C minus Y. And CF4 is equal to X, whatever you stored that as. What do we get for K?
I got 1.63.
Okay, what else did we get? Everyone else, what values have we got?
You know how the initial concentration of carbon dioxide is 0.022, and then it's going down by 0.04. Isn't that a negative?
Yes, you're right, which means, what does that tell you, Sid, based on this question? Either the question is faulty, which is very unlikely for a trial question, or what's more likely explanation?
It's an open system.
Oh, no. The simpler conclusion is we've made a mistake in our calculator use, right? So I want us to check what was a mistake that was made. This is a very annoying task to do, but I promise you the student that is the best at doing this will not ever make a mistake in a calculation question. So I want all of you guys to quickly review this, right? And tell me, where is a mistake that we've made in our calculation? My tip is start from the beginning very quickly, just sub in all the values. Now that you've written it neatly, it should be much easier to resub in and calculate. Give you all context, I finished my HSC Chem exam in about 2 hours, 20 minutes. The other 40 minutes of my exam was just me going through every single question, especially the calculation questions, doing it again, making sure it's right for every single question. And that's what helps you pick up a lot of marks. So let me help you all out since this is your first time doing this, right? So very quickly confirm that your data points are correct. You've got 29 grams, you've got 5 grams, tick and tick. We've got 4 grams per liter, tick, so that's right. Now make sure you go through all of them. Is our number of moles for CO2 correct? When we divide, I kind of jumped it because I expected you guys to have already found it. But if I was to have done this question, I would have written N equals to mass and molar mass. I would have said is equal to 5 divided by 12.01 plus 2 times 16. So is that equal to 0.1136?
Yes.
Good. Next calculation question, right? So we then divided it by 5. Is that equal to 0.2272?
Yeah.
Good. Now go to CF4, right? Is CF4, is its initial number of moles equal to 0.3295? So this 29 grams, when you divide it by CF4, so it's going to be number of moles of CF4 initially is equal to mass and molar mass, 29 divided by 12.01 plus 4 times fluorine, whatever that is. Is that equal to 0.3295?
Yes.
Good. Next, divided by 5. Is that equal to 0.0659? Sid, have you found the mistake?
Yeah. I think it was the concentration, the final concentration of CF4.
Okay, good. That has to be the mistake, because remember, our change in concentration is what we got wrong, which means our initial and final were wrong. Very good. So our x value is not right. What should our x value be?
0.0605.
605? Okay, so here it should be 0.0605. Sure, all right. That's the main thing. And then the only thing that would change here is this. So it would change all your stored values, but in terms of our calculation so far, it would change d minus x, whatever you stored as y. So now re-put that in the formula, and hopefully now it should work out. Because the initial concentration is 0.0659, the final is 0.060, so definitely all the values should be positive now. So good. This stuff, they don't stress enough in school, and it's the boring stuff, but this is the stuff that gets you from a band 6 to a state rank, right? It's whoever makes the least silly mistakes. So I want you guys to get really good at this. The way I tested this is I did every question I got wrong, I redid it. And I tried to get it right in that exam by rechecking. And I made sure my working out was very neat and clean so I could follow it. This is messy. This is what happens after 7 years of teaching. You get a little bit sloppy in your directions. For all of you, when you're doing your calculations, you should be coming straight down. All the equal signs should be directly underneath each other. When you reach the end of the page, you rule a margin, and then you go to the next line of working out. That's what I did during my HSC. Okay, good. Any questions? So what's our K value now? Because this question is meant to teach you something new, which you haven't learned, which is called the reaction quotient. So what is our K value that we get? Let me turn the light on. Akshita, what did you get for your K value?
My system just crashed, so I had to like do everything again. I'm not sure.
That's okay. Anyone got an answer for K? All right, let's do it together, right? We've got our new X value. So the main thing that's going to change is when you store that as X, your D minus X will change. What is D minus X? So your Y, which is your change in concentration, everyone. So we know D is the initial concentration of CF4, which is 0.0659. We're subtracting it from 0.0605. So what do we get for Y? Can someone tell me?
Yeah, I got the KEQ for the question.
Oh, good. What did you get, Sid?
2.77.
Okay. Now, when it comes to K, there's a duality to K. There is the maths side of things, and there's the logical, qualitative side of things. So, Sid, let me ask you, what does this tell you about this story, which is a chemical reaction? So, first of all, Sid, are we in equilibrium?
No.
No, right? So we know our K value for this particular temperature. They've said nothing about changing temperature, so you assume the K never changes. The K is 0.5 at equilibrium, which means the equilibrium constant is 0.5. Whatever we've calculated is not 0.5. And so we cannot call it the equilibrium constant. And it's because our system is not in equilibrium. Does that make sense to us so far, everyone? Whatever we calculated as K is not equal to the actual K value. It is not equal to the equilibrium constant. The system is not at equilibrium. That is the first conclusion I can make. Now, when it comes to naming and wording, let me just explain this to you. Does everyone see how we found a K value, but we weren't sure if it was equal to the K value, which is 0.5, the equilibrium constant? Now, when we're finding this formula for K, but we're not sure if the system is at equilibrium, we can't call it K. This is more of a technical thing, but it's very important. We call it Q, or the reaction quotient. Okay, and that is different to K, which is the equilibrium constant. Can everyone appreciate what kind of question this was? This question was a question asking you, is the system at equilibrium? Prove it with maths. Whenever they ask you to prove a system is in equilibrium, you must find the Q value, which is the reaction quotient, and compare it to K. So when Q is equal to K, Ritania, what does that mean? Is the system at equilibrium or no?
It is at equilibrium.
Very good. So we can say the reaction quotient that we found, and we had no clue if the system was at equilibrium, that's what the reaction quotient is. When you sub concentration values into the K constant formula, but you have no idea if the system's at equilibrium, you call that Q. Yes? And when Q is equal to K at a particular temperature, the system's at equilibrium. Now, what does it mean if Q is greater than K? Like we see in this question here. It's 2.77 instead of 0.5. Then, first of all, Sid has told us it's not at equilibrium. What further information can you gather from this information? Q is bigger than K, Zainul. What conclusion or judgment can you come from this?
It's not going to be in equilibrium.
Yes, that's Sid's already said that, right? It's
Oh.
not at equilibrium. So I'm asking you, what's a further conclusion you can make?
I'm not sure.
Zainul, what does K tell you? I said two words at the very beginning of class that you need to repeat to me and ask you what K is. What were those two words, Zainul?
Was it equilibrium position?
Very good. Now, what can you be told about equilibrium position when Q is greater than K? First thing is that it's not at equilibrium. Does the position of this reaction lie to the right or to the left?
I'm not sure.
Think about the formula we just used. Our value is too big, right? Every system wants to reach equilibrium. That's what Le Chatelier's principle is all about. This system wants to get to 0.5 when you divide its product concentration by reactant concentrations. It is not there yet. It is not at equilibrium. What concentration is too high? What concentration is too low, Jacob? Products versus reactants.
Yeah, so the value of Q would be greater than K, so it would have to lie to the right then, because there's more products than reactants.
Very good, right? So what this is telling you objectively, when you see a Q value bigger than K, is number one, as Sid said, it's not at equilibrium, and number two, since it's a higher value than it should be, remember, what is Q and what is K? It's equal to the concentration of products divided by the concentration of reactants. So what Jacob is telling us is since Q is too big, it means there's too high of a concentration of products and too low of a concentration of reactants. And that is why it is not equaling K. Now, Le Chatelier's principle says that all systems want to return to equilibrium. So actually, though, what would we want to eventually happen to the product concentration and the reactant concentrations to return to equilibrium?
We would want the product concentrations to decrease.
Very good.
And the reactant concentrations to increase.
Very good. So let me ask you this actually, though. How can we achieve that where our product concentrations decrease and our reactant concentrations increase? Which direction should I go in a reaction? Reactants are on the left, products on the right. Which way do you want to go if you want to decrease products?
Left.
Exactly, right? You want to go to the left. You want to use up these products, make more reactants. So the conclusion we've all made today, everyone, is since Q is bigger than K, two conclusions. Number one, it's not at equilibrium. And number two, the reverse reaction is being favored at that point in time. Is being favored. What that means is the reverse reaction right now at this point in time is greater than the forward reaction, so that we can return back to equilibrium. The reverse reaction is being favored to return to equilibrium. And I know some of you must be thinking, Rao, that was very hard to think and logically conclude. So let me show you a very easy shortcut to explain what Q means. Very simple shortcut. A year 3 kid could do this, right? Next time you're asked to compare Q and K, my tip is plot it on the number line. Yes? K is 0.5. That's K. Where was Q, Sid? What was the Q value again?
Not okay. 2.77. Okay.
Yeah, so you remember you just right there, right? So Q is 2.77. Now, Sid, all systems want to return to equilibrium, meaning all systems eventually want their Q to equal K. Which direction in our number line do we have to go to return to equilibrium or K?
Towards the left.
Exactly. So in 1 second, Sid could tell me now in future that the reverse reaction is going to be favored to return to K. Similarly, let's say if Sid calculated this and he told us that the Q value that we got, the reaction quotient, I need you guys to all say this. This is the power of being muted. You can repeat the word 50 times. It doesn't annoy anyone, right? If you don't say it, you're going to forget it by the end of the lesson and you're not going to benefit at all. Say the words. So the equilibrium constant, in this case, is much larger than reaction quotient. So let's say that Sid's found out that Q, our reaction quotient, is equal to 0.2 when K, that's Q, K is equal to 0.5. So again, actually, is the system at equilibrium in this new example?
No.
No, right? So that's the first thing she can tell me. And actually, which reaction is going to be favored at this point in time to return to equilibrium?
The forward reaction.
Easy, right? All she had to do was think, well, Q is less than K. Q always wants to return to K, so Q needs to drive to the right, needs to move to the right to get back to K, right? And so what this means is a forward reaction at this point in time is greater than the reverse reaction so that we can return back to equilibrium. Very good. So all of this is written for you, so don't stress out that we haven't written anything about the reaction quotient. You learn the best through questions. So you're coming back all the way up here, all these fruits, these cool images. Let's go even higher, and we will go. We've done these questions. Yeah. Yeah, this is your theory. So it's all on page 90. Okay, let's read the dot point. Do you understand? Such a verbose dot point. Perform calculations to find the value of K in concentrations of substances within an equilibrium. Use these values to make predictions on the direction in which a reaction may proceed. What this means, all of this Sounds like an essay writer or a poet wrote this dot point. This dot point literally means calculate Q, compare to K, and tell us, is it an equilibrium and which reaction is being favored? That is what this dot point is all about. Okay? And what kind of question will prompt you to use this information, everyone? What did I say? Jacob, what kind of question will you decide? I need to find Q, I need to compare it to K. What will the question usually ask you?
Usually when the system is not at equilibrium, so you just have to find.
Yeah,
you have
or
to compare
the question
it to
will
the
ask
K
you.
value.
Exactly, yeah. So often the question will ask you, is the system at equilibrium? Or determine if the system is in equilibrium. If you ever see a question like that, you will always have to find Q, compare to K, and then comment those two things. Is it at equilibrium? And if it's not, which reaction is being favored? It's that simple. And as you can see here, the reaction for the Q, or the reaction quotient, the calculation for it, is the exact same as the calculation for K. This is no new information for you, right? You just have to do a few more questions. Now, let's do another question. Let's do, okay, don't worry about this little tip up here. We'll come back to that one. It's important for us. I want you to just, it's easy. There you go. Okay. Question 3. Here's Tommy's answer, A, B, C, or D. You'll have about 1.5 minutes to calculate this. While you all are doing this, outside looks very beautiful. I'm going to quickly take a photo because it looks so nice. I know I didn't give you all a break this lesson. That's because we have quite a bit to cover. So feel free to stand while doing this question. Feel free to take a quick walk while you're doing this question as well. I'm happy to let you all have a little bit of a breather. Just make sure you're moving, because if you sit down for too long, I know what it's like because I've been studying for a long, long time. It's so boring when you're just sitting and not moving. So just get up, walk around. Feel free to get some water. And then come back and hit the raise hand icon. Good job, Britannia. Does anyone know any other examples? So I gave you all a very vague example as to using chemistry in medicine, which was in the event that they have acid-base problems, the pH of the blood is very low, we think about what acids could be causing this. And we said in type 1 diabetics, they make ketones, which are acidic. If someone has a stroke or a really big heart attack or a blood infection, the blood becomes acidic. And so that tells us information. But does anyone know any other examples of everyday chemistry that we use in medicine? Especially those of you who are medically inclined. I think Zainul was interested in computer science. Sid was interested in engineering. Rithanya and Akshita, and Jacob was computer science as well. So Rithanya, Akshita, the ideas of using chem in medicine. Okay, so again, I'm on colorectal surgery, which is bowel surgery. A lot of patients are either bleeding from their rectum because of a tumor, cancer, inflammation, infection, and so to rest their digestive system, we tell them not to eat or drink. So actually, if someone's not eating or drinking, what do we need to replace for them? Straight into their vein. what would you want to give them?
Like fluids.
Fluids, exactly, right? And we can't give them pure water continuously because our body has an osmolarity or a salt concentration. If we give pure water, all the ions will shift. That can cause heart problems, brain swelling, etc., etc. So we need to give fluids at the exact same concentration as your plasma, which is your blood, your water inside, and that's about 154 millimoles of
Was
salt.
that hypotension? Was it called that?
Hypotonic. Hypotension
Yeah.
is low blood pressure. So even in low blood pressure, which we get all the time, if you work on if you become a junior doctor one day, half the time on the ward, the nurses will come and tell you, this patient's blood pressure is too low. What do we do? And you just have to go examine them, look at how much water is in them. Do they not have enough water? Which means their blood pressure would drop. In that case, you'd give them fluids. And then I need to think about what concentration of fluids do I need to give? What ions do I need to replace? Order the bloods, check all of that. So that's everyday chemistry that junior doctors will be using. Good. All right. So what did we get for question 3, Jacob?
Yeah, I got D.
Good. Britannia, what about you?
I got D as well.
Good. All right. I'm happy to move on and not explain that because unless someone wants me to, but I think that was quite a straightforward question as long as you applied the 2 things that we spoke about. Very good. Okay. This document is just telling you, can you explain how temperature affects K? And we've already done an exam question on that, where I gave you an exothermic reaction and I asked you how increasing or decreasing temperature would affect K. So that has literally taught you that dot point, okay? Now, this dot point here is very high yield. Okay? I want you guys to all circle this one. And the reason it's high yield is because, first of all, this is the second experiment that you're learning for year 12 chemistry. The first one being that dot point where you had to model static and dynamic equilibriums, and then they gave you specific reactions. Do you all remember the cobalt chloride equilibrium we looked at, where the solution went from blue to pink, etc.? This is another equilibrium, and this one is very important because this is the equilibrium which we will use to calculate K through an experiment. The K is not just an imaginary theoretical word that we throw around and calculate that we actually can't find. We can find K. And this experiment will show you how to calculate the equilibrium constant for a reaction. Now, Zainul, static or dynamic equilibrium? What do you see up there for iron plus thiocyanate?
Dynamic.
Very good. It's because both arrows are going back and forth. Very good. And a bit of a extra additional question, Sid. What do you call this compound that has square brackets around it, has a charge, and is colored? Do you know what we call this?
Complex.
Very good, right? So whenever metal ions have a characteristic color, they more than often form a complex. This is also a complex. This is not the correct way to write Fe3+. What actually happens is Fe combines with 6 water molecules and creates an overall charge of 3+. But for now, we're going to forget about the water. And so it just looks like Fe3+ to us. But the point I'm trying to convey here is that whenever a metal ion has a characteristic color, like copper, like iron 2, like iron 3, it's going to form a complex in water. Okay, and a complex is just when the metal ion binds to other things and has a net charge and has a unique color. Very good. Okay, now to understand this experiment, we need to first understand a very important piece of technology called colorimetry. Can you guys hit the raise hand icon if you've studied colorimetry, you've gone through it before in school, etc., etc.? Okay. When I first learned colorimetry, I thought, yeah, this is cool, but it's not crazy cool. And what you learn later, and this is very interesting for the engineering people and also the coding people, we use variations of colorimetry to measure the concentration of various products in blood. So blood testing uses principles of colorimetry, where we pass light through the blood sample. We measure the concentration of metal ions, we measure the concentration of toxic substances, and we use it to save lives. And what we're trying to get to in medicine right now, you guys might not suffer from this. Maybe your parents, maybe you've seen family members who have. That at hospital we prick people and we take a lot of blood. And it's painful, it hurts, there's bleeding, etc. What we're trying to work on now is to create a machine that can analyze a drop of blood ideally, give you all the information you need, compared to having to, put a really long needle through them, hurt them, collect 20 ml of blood, etc. Right? And that's based on the principles of this colorimetry. So I want you to pay attention, because engineering people, you may have to use this in your future. Coding people, you may have to code the software for this tech if it comes out, right? So when it comes to colorimetry, it's based on spectroscopy, which is the umbrella term. Sid, have you ever heard of the word spectroscopy before?
Yes.
Any idea what spectra refers to?
Light.
Very good, right? What does oscopy or metry mean? The general terms.
I'm assuming it's like that, something that shoots out light to measure something.
Yeah, spectroscopy or spectrometry, metry meaning measure, is a study of light and matter, right? So spectrometry is when we shoot light at a sample and we measure how that light changes. Spectra is a light. Oscopy or metry is a study. So we're studying how light interacts with matter. Now, very, very important to understand this. Right now, all of you can see my shirt right now is blue. What color is the shirt reflecting, and what color is the shirt absorbing, Zeno? So white light from this roof is shining on my shirt. What light colors is it absorbing, and what light colors is it reflecting into your eyes?
I'm just gonna assume it's gonna be the same white light.
If this shirt reflected white light into your eyes, you'd see a white shirt. You don't, so it's not
Be
white.
Like, if it's your shirt, I'm gonna dark blue.
So is this shirt absorbing dark blue or reflecting dark blue?
Reflecting.
Very good. So in reality, this shirt is every color but dark blue, because it's absorbing every other color, and it only reflects blue light, hence why you see this shirt as blue, because that blue light is going into your retina, the back of your eye, and you're interpreting that. Very good. It's the same principle for colored solutions. Like Shita, copper sulfate, CuSO4, is a blue colored solution. Can you tell me what wavelengths of light does that solution absorb? And what is the one wavelength of light the solution would not absorb?
Would it absorb yellow? Was it? Because it's
Very
opposite.
good. Exactly, right? Very important principle. So what I'm trying to get at here is spectroscopy is a study of light and matter. Colorimetry is one specific example of spectroscopy where we're not using any light, we're using visible light. Because remember, there's radio waves, there's X-rays, there's gamma rays, the entire electromagnetic spectrum, which varies by frequency and wavelength, is humongous. Colorimetry is only using a very small part of that spectrum, visible light, and shooting it at matter, right? And so for us to decide what color light we shoot at matter, we actually pick the inverse color of that solution. I want you guys to get your phones out now. Rare opportunity for you to go on your phone in class. Search up color wheel. Go on Google and search up color wheel. You do not need to memorize this color wheel. But the color wheel tells you all the opposite colors of solutions. So if you look at blue, the complementary inverse color of blue is about orange/yellowy, right? So we just use yellow light. And so the principle here is for a colorimeter, it's a little machine. It looks like this. Let's see if I've already got an image for you. There you go. Right? So all of this is inside the colorimeter, and it has a little slate for you to drop a little test tube of colored solution. Now what's going to happen is inside the colorimeter, there is a white light source. The white light is then released. And then forget about the lens. The lens is just amplifying the light. What we have is a monochromator, right? A monochromator will diffract or bend light. Now, yeah, I'm sure you've all seen rainbows. In rainbows, what's really happening is white light from the sun is diffracting or bending because of raindrops, and you see it splitting into every single color, and it looks beautiful, right? So a diffractor here is doing the exact same thing, splitting that white light to all the colors. And then what you have is a wavelength selector or a slit. Now, you can adjust or change this, but you will pick the wavelength selector that selects the complementary color to the solution. But just as Akshita said, for a blue colored solution, the wavelength we'll be using is yellow. Hopefully you all have the color wheel in front of you. Let's say, Jacob, I was selecting a green color solution, such as iron hydroxide, iron 2 hydroxide. What color would you want the wavelength selector to pick for a green colored iron 2 hydroxide solution?
Red.
Yeah, red. That works well. Like red, pink, possibly purple, but yeah, red works very well. So there's actually been specific MCQ questions that have tested this, right? So it's important to understand this principle. Very good. Now, the next important point, this makes very logical sense, is the more atoms in that solution, the greater that this light will be absorbed. So if I have one atom of copper sulfate, for example, the yellow light will be absorbed to a very, very tiny degree. But if I have a lot of atoms in this fixed volume, a lot of particles, then there'll be a greater absorbance of this yellow light. And so finally what happens is this digital meter is going to pick up the light intensity before it passed through the sample and the light intensity after it passed through the sample to calculate what's called absorbance, which is the degree of light absorbed. Okay? And as I mentioned to you guys, the more atoms in that test tube, the greater the absorbance. Atoms in a fixed volume, what am I referring to? Number of atoms, number of particles in a volume. What is that calculation?
Concentration.
Very good. Perfect, Akshita. So the greater the concentration of this colored solution, the greater the absorbance. That is all colorimetry is going to tell you. Does that make sense to everyone so far? So hopefully you all understand colorimetry. What is it? It's an example of spectroscopy. We'll be passing light-specific wavelengths through colored solutions, and we'll be using this to determine the absorbance. And from the absorbance, we can determine the concentration of the solution. And that's because absorbance is directly proportional to concentration. What I just wrote is in fact a law in chemistry, and we'll talk about that shortly. Before now, I just want you to understand the absorbance number you get is directly proportional to concentration, right? So if it was 0.7, you know there's a much greater concentration of substances, almost linearly, right? Very good. Any questions so far? Okay, done a lot of talking. So now what I'm going to do is I am going to let you read this method and try to understand what we've done. Because processing and digesting information is super important. So I want you to imagine this is the first time you've seen this experiment. Can someone explain to me in simple terms, what the heck are we doing? You have about a minute, then I'm going to start asking people. So hit the raise hand icon once you've started to understand what's going on. Okay. Anyone else? I see Akshita's got an answer. Anyone else know what we're doing here? Does it make sense at all? Good. All right. I will get Ruthania. Ruthania, do you want to explain it to us? What are we doing in very simple terms, right? Imagine your school friends are sitting around you lunchtime. Want to know what's going on with this document. How do you explain it?
Basically, we're conducting the experiment to determine the constant value of iron thiocyanate.
Good. Okay. How are we going to do that?
It says that you have to make the solution and you're going to put it into the colorimeter thing.
Sid? Actually, I've asked Sid a lot. Let me ask Jacob. Let me explain it. What's going on in this experiment?
Okay, so we're basically just getting the iron nitrate, and we're using the pipette to transfer it into a flask, and then we're getting the potassium thiocyanate, and we're doing the same thing. So we're going to transfer that into the same flask, I'm guessing, and then from there we can then use the color to find the concentration. Yeah.
Good. The only way I would structure this to help you all out is rice table wise, right? So let's say I add 1 mole of iron nitrate, 1 mole of potassium thiocyanate in 1 liter of water. Let's keep it very simple, right? I straight away know my initial concentrations of iron and thiocyanate. And I've added 1 mole of iron 3, 1 mole of thiocyanate in 1 liter. So I know the initial concentrations. I've got these initial concentrations of iron and thiocyanate. Whatever I add is going to be the initial concentration. But then what's going to happen is these particles are going to collide and get used up and form some of this product. And we have no clue how much is being used up to form iron thiocyanate unless we use colorimetry. What colorimetry is going to help us do is calculate an absorbance value for the final solution that's at equilibrium. So does everyone agree? Whatever you add in that solution is going to be the initial concentrations of iron and thiocyanate, and whatever you measure in colorimetry is going to be the equilibrium concentration of FeSEN2, the product. Doesn't this just look like a rice table question? You've been given initial concentrations of your reactants. You've been given equilibrium concentration of a product. Does everyone agree if you've been given initial concentration of iron and thiocyanate, you've been given X from colorimetry, what colorimetry will tell you is an absorbance value that you will use to calculate concentration. You can put it in a rice table and solve everything else out, right? We know at time equals to 0, there's 0 iron thiocyanate. So we can say the change in concentration of iron thiocyanate is just its equilibrium concentration X. And we subtract X from everything else, and now you've got all the equilibrium concentrations, you sub it into K. This is very high yield. The reason is, first of all, it's an experiment. Second of all, students often forget it, so they love adding it in your exams. And it also links very well to spectroscopy, which is studied in Module 8. Remember when I told you all colorimetry is only one example of spectroscopy? This is what I mean. There's many more examples. There's mass spectroscopy, infrared spectroscopy, NMR spectroscopy. You learn all of that Module 8. This is a good window into learning about those things. Very good. Another tip, this is in your exam at the end of this term, giving you a question, so make sure you revise this. Good. All right, what we'll do is we'll stop right there, and what we'll also talk about is previous lesson. Does anyone have any questions from homework for the previous lesson? So from the neat paper, any of these questions? We can always go through it next week because we've already hit time for today. But if you have any questions at the beginning of class, bring it up. We'll go through it together. The other thing is, can you all hit the raise hand icon? Are you doing these trial questions at the bottom of the booklet? Good, good. You need sample answers too. So this week I'm going to be putting all the papers on the drive. This is my last week at hospital for the year, so I'll be much more free after this. Just this week is very busy. So I apologize in advance for any late replies. Just give me about 2 days and I'll get to all of you for whatever messages you send. But by the end of the week, you'll get access to all the papers. Just find the paper, mark yourself. Okay? If it still doesn't make sense, bring it up in class. We'll go through it together. Okay. Good. Any questions about studying, stress, anything about Year 12? I'm here not just for chemistry, but you know, I also sat the HSC, so I know it's stressful. I know it's a busy year for you all. Anyone have any questions at all before we finish off for today? Jacob?
Yeah, I had a question. When are we gonna start with the 4th inquiry question? So the one after this.
Is that KSP, Jacob?
Yeah.
KSP likely next week, because we finished K, we finished Q. We would maybe do, yeah, we've quite literally finished K and Q, which is the main components, and KSP is the final inquiry question. So we're going to be finished module 5 in about, I think, 2-3 weeks max. Okay.
Okay. Yep.
Good. Is that because of your assessment task?
Yeah, because I had a question. It's like a KSP question. So,
How
the
about
thing is,
if you have a question, post it in the Teams channel. Let the others, your peers also give it a go, and tag me as well, and I'll also give you a verbal explanation for that question.
Yeah,
Okay.
yeah, and but the questions from the from this year's HSC, it's like the very last one, and it's on KSP. And our teacher wanted us to do it, but like, yeah, it's a bit hard. So
send me your working out or your specific question.
Yeah.
We'll go through it. But
Right,
sounds
sweet.
good. Next week we'll go through KSP. Okay.
Okay.
Good. All right. All right, guys, have a good week. Make sure you're doing something outside of studying, but enjoy. See you all on Saturday.
See you later.
Thank you.
I have a question.
Bye.
Yes, bye. I'll wait for Akshita, question?
No, it was me.
Oh,
Do you
Rosanna?
know if there were any depth study ideas to do for Mod 5? Because we're getting our notification on Monday.
What do you like modeling?
I'm not sure about anything, but I mean, Mod 5 kind of seems odd for a depth study.
You'll be modeling equilibrium, or you'll be using an industrial equilibrium. So your depth study will either be create a model to represent dynamic and static equilibrium. You can use like computer tech, program, water and cylinders. I've seen a lot of variations of this. Then your other one could be possibly an industrial chemical equilibrium and the factors that affect it, and do research on that. The Haber process, there's the Ostwald process, there's also the contact process. All of them have equilibrium, so you will have to do either or. Possibly something about cycads, depth study on the cycacin toxin, or your depth study could be researching like the chemical reactions, the ones that you looked at, steel wool combustion, cobalt chloride, etc. But it's very limited to those things. Okay.
And also for bio, I'm doing Mod 7 at school.
Do you
And
want
I was
the
like,
Mod 7 booklet?
yes, please.
Sure, we can arrange that. And if you have any depth studies or assessments, just message me, or in the 5-minute break we can go through your depth study or your exams in Mod 7. Okay.
Yeah.
Good. Sid,
Thank you.
Yeah. Oh, okay.
Yeah, question.
Yeah. So with my assessment, we have to draw a hand-drawn model of weak, strong acids and bases, concentrated, dilute. Is there anything that I would need to include?
There's a lot to include. First, you should show me your models, but the InFocus textbook has a really good example, and my notes should also have a very good example of concentrated, weak, and strong acids. What's the definition of strength of an acid?
The degree of ionization.
Very good. So you just want to show HA being 2 particles, and then all of HA breaking up into H plus and A minus. That is a strong acid.
Yeah.
A weak acid, 20% of the HA molecules would break into H plus and A minus. And then concentrated, just the number of particles, right? So a lot of circles would represent H and A. 20 particles of HA versus 2 particles of HA represents a strong versus a weak. Sorry, concentrated versus a dilute acid. That's it.
Okay.
Yeah, that's pretty much what you would have to show. And maybe use the Bronsted-Lowry notation. So instead of H plus, show H3O plus. Just send it across to me, okay? We'll have a look.
Yeah. Is there anything else I would need to know for a skills assessment?
For Mod 6?
So our experiment was for Mod 5 for the solubility rules.
Okay, your experiment is solubility rules. In terms of content, you should know common ion effect. An experimented test for the common ion effect. You should know how temperature might affect solubility. It's various, but usually temperature will increase solubility for a salt, and why that does that in terms of the bonding. You should know accuracy, validity, reliability for the specific experiments, so pretty much a discussion ready. What a control looks like, and then graphing, how to graph, tabulate data. That's pretty much it. And then if they give you a table to comment on accuracy, and even precision as well, because accuracy is how close you are to the true value. Precision is how close the values are to each other. So just knowing all those differences.
Yeah. The thing is, with the independent variable, right? You're changing the anions and the cations. So would you have 2 independent variables?
In what example? What's the experiment?
So it's just like a grid table where you do all the cations on the top, anions, and then you test them on like a spot plate.
So if they fall and precipitate or not. There's no control then. For that kind of experiment, there's no control. You're just testing solubility. You don't need to go into the depth. A control is when you have one specific independent and a dependent, and you just remove the independent. So in that case, not really a control. So know your solubility rules as well. The little trick is your HSC Chem data sheet. On the back, every single compound that has a KSP is insoluble. Everything else is soluble.
Yeah. Okay.
Good. Yeah.
That's all.
Let me know if you have any other questions, okay?
Yeah. I'll send you the model tonight for that.
Sounds good. All
Yeah,
right.
okay. Thank you.
Yeah.